We're now going to add to what we saw for bonding from Lecture 7, specifically talking about Lewis structures. So we'll look at Lewis structures that are exceptions to the octet rule. We'll talk about how to calculate formal charge for a Lewis structure and what that tells us about the structure, bond energy and bond length and how those are related, and then finally resonance structures. So to start, let's look at some exceptions to the octet rule. The first type of exception to the octet rule is called an incomplete octet. These are atoms that in their bonding, they do not have 8 electrons. And we'll see why that is perfectly fine for those elements. So first off, looking at boron. Boron will only attract 6 electrons to itself in a bond instead of 8. So if we look at this Lewis structure here for BF3, each fluorine has 8 electrons around it, but this boron in the center only has these 2, 4, 6. So we may predict that one of the fluorines would create a double bond with boron to give it 8, but in fact it remains just like this with only 6 around it. And that is because boron only has 5 protons. So its ability to attract 8 electrons to itself in bonds is very unlikely. Instead, it's just going to have 6 electrons around it. A very similar example that I don't see that they're giving you in the notes is the element beryllium. Beryllium only has 4 protons, and so beryllium really can't attract more than 4 electrons to itself in a bond. So it's going to have its octet complete with just 4 electrons instead of 8. The other exception is the opposite of that, and that is when an element attracts more than 8 electrons to itself, and this is called an expanded octet. This can occur in periods or rows on the periodic table 3 through 7. So elements in periods 3 through 7 can bond with other atoms to end up with more than 8 electrons in their octet. And they can do this because elements on the 3rd row and lower have a d orbital. So you know, if we look at the electron configuration, it's 1s2, 2s2, so on and so forth. And after 4s, we have a 3d. So 3 is the first period that has the d orbital. And due to the fact that it has that d orbital, it can put extra electrons in there, and those extra electrons cause it to have an expanded octet. Also, if you think about elements in periods 3 through 7, they have lots of protons in their nucleus, so they could attract more than 8 electrons to themselves. The most we see still is 12. So that's the most we'll see in bonding, is an element having 12 electrons around itself. Here's an example of phosphorus pentachloride. So you have a phosphorus surrounded by 5 chlorines, and you'll notice that if it is surrounded by 5 chlorines, that's 5 bonds, so that's 10 electrons around it. Some of these electrons would be placed in the 3d sublevel. Sulfur can do the same thing. So this is sulfur hexa, I guess it's 6, hexafluoride. Those 6 fluorines around sulfur mean that it has 12 electrons around it. And so again, those extra electrons could go into the 3d sublevel. If you look, what they're showing you here is the electron configuration just for sulfur as an element. So it's 3s2, 3p4. But if it has 12 electrons around it, then that's going to mean more than these 6 that are shown here, because the 12 around it are in the valence shell. So there's only 6, but it has 12, because it borrows them from fluorine, right? And so those extras go into the 3d, and that's easy because 3d and 3p have very similar energy. Right? Again, we see xenon here. Xenon has 4 bonds around it, that's 8 electrons, and then there were 4 electrons left over, so those also belong to xenon, and so that means that xenon has 12 electrons around it. Well, xenon is on the 5th row of the periodic table, so it already has a 5s and a 5p, so the extra electrons would go into the 5d orbital. Next thing up is something called formal charge. Alright, so we're going to define what it is and kind of practice calculating it. In some cases, the atoms in a molecule can be arranged or assembled in different ways when you draw the Lewis diagram. So the formal charge is calculated to tell you which of those structures is the most stable or the most likely. The sum of the formal charges on each atom will be 0, so that's one of the rules. When you calculate formal charge, the sum of the formal charges will be 0 for a neutral molecule, and the sum of the formal charges will be equal to the charge if it's a polyatomic ion. When you're looking at formal charges, this is the way that you tell which structure is preferred. The more likely Lewis structure will have a formal charge or formal charges that are closer to 0 for each atom. So if all your atoms could have a formal charge of 0, that would be awesome. But if maybe one has a -1 and one has a +1 in a structure, and in another structure you have -2 and +2, the ones that are closer to 0 are going to be preferred. If you do have negative formal charges, they should be on the more electronegative element in the structure. Okay, so we'll look at some examples to make sense of this, but these are your basic rules. You want to minimize formal charge, so be as close to 0 as possible. Alright, so first off, how do you calculate formal charge? Formal charge is simply the number of valence electrons that were assigned to that atom. So how many valence electrons does that atom have according to the periodic table? How many valence electrons did it bring in to the compound? Minus the number of electrons that are assigned to that atom in the Lewis structure. So that number will be the number of lone pairs around the atom plus the number of bonding electrons divided by 2. Because a bond is 2 electrons, but it's being shared. So when we're doing formal charge, we'll assign one of those to each element in the bond. Okay, so hopefully this will make sense as we do the examples, but this is the basic equation that you can refer back to. Alright, so let's look at 2 different structures for a simple compound, nitrogen trichloride. So we have the option of putting the nitrogen in the center, like you see here, or maybe the chlorine goes in the center, like you see in the second example. Which structure is most likely? So if you're asked this question, you can't just say, oh, this one, because it's more symmetrical, for example. Okay, the explanation for why something is a more likely Lewis structure has to do with the formal charge. So let's calculate the formal charge in both of these structures and see which one fits our requirements better. Okay, starting with this first, or I guess this is the second structure showed us, but we're going to look at this structure with a chlorine in the middle. So first for the nitrogen. Nitrogen has 5 valence electrons. Chlorine has 7. So we'll put those on the valence electron line. Then how many electrons are assigned to the nitrogen in the compound? So nitrogen has 1 bond to it. And we know that's 2 electrons, but we're going to pretend that one of them belongs to nitrogen and one of them belongs to chlorine. So that means that nitrogen has 1, 2, 3, 4, 5, 6, 7. If we count 1 from that bond, 7 electrons assigned to it. So 7 go there. Okay, and we're going to subtract these. Then in chlorine, let's do the chlorine in the center next. So there's chlorine in the center. I'll mark these with, let's say, yellow. It has these 2. So there's 2 electrons assigned to it, and then 1 from each of these bonds. So 2, 3, 4, 5. So minus 5. And then these outer chlorines, I'll do those with a red. They have 1 from their bond. each, and then 2, 4, 6. 2, 4, 6. So each of those chlorines is assigned 7. Minus 7. Alright? So then let's look at how that math turns out. So for the nitrogen, it would have a formal charge of -2. Chlorine would be +2. And each of these other chlorines would be 0. Now these two being 0, that is awesome. Okay? But these being -2 and +2, that's not really minimizing formal charge. Okay? Let's see if the other structure does a better job of that. So here's those values again, if you want to jot those down. They did the chlorine in a different order. So this chlorine on the end here is their center. Okay, and we did it in a different column. So no big deal there. But you see the nitrogen has a -2, the chlorine has a +2. Those high formal charges mean that structure is not likely to occur. Let's look at this structure, okay, the alternate one with the nitrogen in the middle. So same thing as before on our valence. Chlorine has 7 valence, nitrogen has 5. Now for the electrons assigned. Each of these chlorines is identical. So each of them has 6 dots and 1 bond and 3 bonds. So 2 dots and 3 bonds, that's a total of 5. Okay, so this is looking pretty good. Let's look at those numbers, how they play out. So each chlorine is assigned 7 and had 7 valence. Each nitrogen is assigned 5 and had 5 valence. So that means the formal charge in this molecule is 0 across the board. So this would be the more likely structure. Alright, what about these two? This is CSN, the compound, or excuse me, the polyatomic ion. We see it has a -1 charge on it. So would it be more likely for the sulfur or for the carbon to be in the middle? All right, let's calculate formal charge to decide. So first off, we're going to look at the structure with the sulfur in the middle. Carbon has 4 valence, sulfur has 6, and nitrogen has 5. All right, and then let's look at what's assigned. Carbon has 4 dots and 2 bonds for a total of 6. Sulfur has 4 bonds, so that's 4. And nitrogen has 2 bonds and 4 dots for a total of 6. So we subtract those, and we get formal charges of -2, 2, and -1. Notice that these formal charges do not add up to 0. So -2 and +2 and -1, they add up to -1, which is the charge on the polyatomic ion. That's a rule of formal charge. So it's kind of a way to check your work. But these formal charges are not really minimized, and the -2 is on carbon. That's not the most electronegative element in the structure. So this structure is not as likely to occur. Let's check the other one and see if it's more likely. Okay, carbon in the middle. Carbon has 4 valence, sulfur has 6, nitrogen has 5. Picking up on the electrons assigned, that carbon in the middle has 4 bonds and no dots, so that would be a 4. The sulfur has 4 dots and 2 bonds, that's a 6. And the nitrogen has 2 bonds and 4 dots, that's also a 6. We subtract, and we get 0, 0, -1. Those formal charges are minimized, and the -1 is on nitrogen, and it is the most electronegative element in this structure. Alright, next example. Draw the Lewis structure for sulfate polyatomic ion and check it using formal charges. So we're going to think back to last section on drawing Lewis structures, and the first thing we're going to do is to count the total number of valence in the polyatomic ion. So we have sulfur with 4, each oxygen with 6, and we're going to make sure to add 2 because there's a -2 charge. So we have 32 valence electrons. We'll put the least electronegative one in the center and connect the others to it with single bonds. So we have our sulfur in the middle and the oxygens around it with single bonds. Now, the reason sulfur is in the middle is because it's less electronegative than oxygen. We're then going to complete the octets for our terminal atoms, those on the outside. So we put 6 more electrons around each oxygen. Add up the electrons we've used. Remember there's 2 in each bond, and then 6 around each oxygen. So they do 4 times 8, or a total of 32. We have no electrons left to put on the center atom. Alright, and now we're going to check our formal charges. You see the arrows here where they're doing the calculations for each oxygen. So each oxygen has 6 valence, minus each of these oxygens has 7 electrons assigned to it. So each of these oxygens has a -1 formal charge. All right, let's look at the sulfur in the middle now. Sulfur has 6 valence electrons, and there are 4 assigned to it in the 4 bonds. So that's a +2 formal charge. Alright, now this is kind of a new step that maybe we wouldn't have thought of before, but it says to add multiple bonds or perhaps change the arrangement to eliminate formal charge. So if we go back, how could we make the formal charge of this sulfur go down closer to 0 from +2? Well, if it had some more bonds, if we could subtract a number higher than 4, then maybe this would come down to 0. So if sulfur had 6 bonds, that would be good. Now, can sulfur make 6 bonds? Well, it's in period 3, right? So any element in period 3 or below can make, 5, 6 bonds. And so if we take sulfur and give it a double bond in 2 of these places, that's going to be 6 bonds. And 6 minus 6 is 0. So that would bring sulfur's formal charge down to 0. These oxygens, would they like that? So let's think. They have 6 valence minus, this is going to be 4, 2. So 6 minus 6, they would be 0 as well. So that change would minimize the formal charge. Now you're still going to have some formal charge because you have a -2 charge on the polyatomic ion. So these outside oxygens will still have a -1. But think, these double bonds can move, right, to the other oxygens and minimize their formal charge and move back. So we'll talk about that change in a minute. Right? But you see how that shift that we wouldn't have thought about in pre-AP, because that's too many bonds, we would have said, but it actually minimizes the formal charge and is the preferred structure for sulfate.